Good, good evening, everyone. I'm here in the chat room. Let me show you one thing. Let me show you one thing quickly. Look at that. Chat room. You know what time is it? 8:27. 27 minutes past 8. 8 is the time that I'm supposed to start this chat room. And you know what? That's me there. That's only me. Isn't that disturbing? It's very disturbing. The class is absent in the chat room. But anyway, so that's my reality and I have to live with it. That's the whole point. We live with reality. And somebody asked me to do this problem. And so I'll take the opportunity and work on it. So basically, the situation is you have Mr. Robin. His mass is 55 kilograms. Robin. Mr. Batman has a mass of 90 kilograms. And they are not moving. So when you see this word motionless, it means um, both in the x and y direction, acceleration is zero, right? They are not moving, acceleration is zero. If they move with constant velocity, acceleration is zero too. But let's work on free body diagram here. If you take Robin, what are the forces acting on Robin? You have gravity on Robin, and that is basically his mass. And I will drop the units here just to go quick. Times g. Mass times g is the weight of Robin. And he's holding on a cord. See that? He's holding on a cord. So the tension of the cord, I'm calling TR because it's T of Robin. So it's such that since there is no acceleration, remember I like to write down any extra information I have. Acceleration is zero. So since acceleration is zero, it means the tension force and the gravity force are the same. They cancel out. So the tug war is such, this tension is equal to the weight. So tension in Robin is equal to its mass times 9.81. And this is in Newton. Okay, let's look at Batman. So Batman is holding the cord right there. So if you take this point out, and I put it right here, and then I say, okay, which forces are acting on it? So I have Mr. Batman holding on it. So in other words, if I take either this point, or if I take Mr. Batman, I think it's easier. So let's take Mr. Batman and isolate Mr. Batman. So I have his weight, so which means the force of gravity, Mother Earth, is pulling him down. It's 9 kilograms times 9.8, right? This is in Newton. But look at this. His hands are holding a cord. So this cord is keeping him up. So tension in Batman. So he's not moving, which means tension in Batman is equal to the weight, right? It's cancel out. Okay, good enough. So tension in Batman is the force that is holding him up. Now, if you look at the cord itself, so here's the cord. So, see, this free body diagram is free body diagram of Batman. This is Batman, right? Batman is what I'm putting right here. So this is Mr. Batman. See, this his mask has a little, bat ear, and he has a cape. It's right here, the cape, and he has his little boots right there. So this is Batman. Now, if you do the cord, now is a different situation. If you do the cord at this point right here, right? Take a piece of cord. So what happened? The cord is being pulled down. Oops. Is being pulled down by Mr. Robin. So the tension on the cord is right here, is the TR. So the tension in the cord right here is TR. That's what we be utilized here. Now, if you go to the cord up here, this one, so this tension is withstanding Mr. Batman, and as you can see, it's also withstanding what I'm calling TR. And TR is equal to the weight of Mr. Robin. So the tension has two values. The tension in the cord has two values. One is right here, and that tension is equal to the weight of Robin. The tension up here is equal to the weight of Robin plus the weight of Batman. So it's different. Okay. So I give you a case so you can think about it. Imagine now there is an acceleration involved. Remember I mentioned this in class? You have a cord, have a box, and I have another cord, and I have another box. Box 1, box 2. Box 1 is 10 kilograms. Box 2 is 20 kilograms. And this elevator has a cord. This elevator is moving up with an acceleration given. Let's say, I don't know, 1 meter per square second. So it's just starting moving up. So what are the forces acting on block number 2 and block number 1? What are they? So when you do a problem like that, you also do what I just did, the Newton's second law of motion for block 1 and block 2, except that in this situation, you have to include the fact that sum of forces is not equal to 0. It's equal to mass times whatever acceleration I give you. If it's 1 meter per square second, is the mass you got in these blocks, times 1 meter per square second. I think I mentioned this type of problem in the book, in the classroom, in fact. Okay. So a friend of yours, colleague of yours, asked me to solve this problem, and that's what I'm doing. I recommend you to get familiar with these problems and try to do yourself. If you can't, if you bump into some problem, you can't do it, you can email me and I can try to work something out with you. I can do it for you. Like I just taped this this material, okay? And